very much for the invitation. It is great to be back here after 10 years. So mainly in these 3 lectures, I'll talk about these 4 papers with various collaborators. The first 2 papers, they are with Tom Hardman and Sachin Jain, who was a postdoc here. The third paper is with Tom Hardman and another grad student, Amir. And the fourth one with Tom and Nima, who is another grad student, and Amir.
This grad student called Nima Afghani, is it?
Yes, Nima Afghani.
He needs to add one more, whatever syllable to his name. Anyway.
Today I'll mail. Yes.
You also make it head. Then he has to stop replying to you.
I'll convey that. So today's lecture will mainly based on things that people used to know in 60s and 70s, but somehow we all forgot. And today it's more or less will be a review of things that I'll need on Friday and next Wednesday. So in the life of a high energy theorist, there are certain things which are sacred. For example, if you are working with QFT in Lorentzian signature, it better be unitary, causal, and Lorentzian invariant. Similarly, if you are working in Euclidean signature, it must be reflection positive, which I'll explain later. Permutation invariant or crossing symmetric. And obviously Euclidean invariant. Now from the title, it is clear that I'll mainly focus on this particular property. For obvious reason, causality is a Lorentzian concept, because you need to have a notion of light cone to even talk about causality. But the 2 things that I'll try to stress in these 3 lectures, the first one is a theory can be causal in the vacuum state, but it can violate causality in non-trivial states. So in quantum field theory, causality is a statement about, it's an operator statement. So a theory has to be causal in any state of the theory. And I'll also stress.
Sorry to interrupt, but is that, can't you create any state out of the vacuum in some sense? Is it really not enough to demand all correlators vanish outside space-like separated whatever is your definition for that? In the vacuum, that's not enough?
That's not sufficient, because like I'll actually that's the important part of the lecture. So I'll talk about that today.
Sorry, just one more interruption. What does it mean for something to be crossing symmetric in Euclidean theory?
So by crossing symmetric, I mean basically in the Euclidean signature, basically you're allowed to switch the ordering of the operators. So basically you can expand in S channel or T channel. Finally, you should have the same answer.
So there's some, so you're putting in some requirement of an operator product. If you were just given correlators, correlators just there.
Yes. So basically, when I'm saying it's crossing symmetric, what I mean is basically basically the correlator is permutation invariant. I am allowed to change the ordering. That's it.
Okay, so if you've got bosonic correlators, it doesn't matter in which order.
Yes,
you put it.
exactly. Yes.
Just that it's a function.
Yes, precisely.
Why isn't crossing symmetry a constraint on Lorentzian QFTs?
It's not a.
Because operators may not compete.
Yeah. So basically.
Sure, but that's like a analytic continuation version of crossing symmetry.
Yes, that thing is there. Yeah, that's basically a consequence of Euclidean crossing symmetry. So basically, if you start with Euclidean crossing symmetry, then if you perform the same analytic continuation on the both sides, you should get the same thing. Yes. So that's a consequence of Euclidean crossing symmetry.
But in Euclidean space, he has in mind something much simpler.
Hmm.
Yeah.
And I'll also stress on one more thing, that requiring the theory to be causal in every state of the theory, it can actually impose strong constraint on different QFTs.
Like for example,
Yes.
we know that in GR we can have closed time like curves.
Mm-hmm.
That doesn't mean we should is the statement that looking at that being a solution of the theory,
Mm-hmm.
it is a possible solution but physically not maybe acceptable.
Mm-hmm.
Should we decide to throw a GR on this based on that?
There actually there is some disagreement about that, in the sense even after the paper by Kamano, Edelstein, Maldacen, and Zaviadov, there are gravity people who said that that's not sufficient. So as far as I know, that debate is still going on. So I don't have much to say about that, but yeah, that's a problem. Yes.
Maybe you can discard the closed time-lapse solutions.
Okay.
So unitarity is something which can be stated in terms of the S matrix,
Mhm.
just in terms of asymptotic
Mm-hmm.
properties. But for causality, you have a statement. I mean, you have to come inside and make some statements.
So by
Or
yeah.
do you have some, like asymptotic statements?
So this by causality, I mean micro causality, in the sense that commutators of space-like separated operators should vanish. So that's the statement of causality.
That's your definition.
Yes, yes, yeah.
He's working out a QFT, not gravity. Simpler.
Let me give you two examples of the fact that causality can actually constrain different theories.
I think he's going to work in CF.
Also, is it interesting to know like all these three requirements?
Mm-hmm.
Are they like mutually exhaustive or things like that? Like
Do you mean?
can any one of them imply other?
There is a statement, I don't think there is a proof, that basically unitarity and causality, they are not entirely different from each other, in the sense that, for example, the theory that I'll consider right now, that del phi to the power 4 interaction, you can actually state the problem in terms of causality or unitarity.
But possibly, I think the statement is if any one of them is violated, then it's bad.
Yes, yes. So, yeah. Okay, let me now consider this particular theory in D dimension. I have the standard kinetic term, and a term.
Are we going
Yes.
to talk mainly about conformal field carriers?
Not today, but yeah, basically today I'll just talk about any QFT, and then I'll use that.
And just to be totally clear, when you say unitary, what in practice will you mean?
So in terms of correlator, what I mean is that if I can write down any correlator as a norm of some state, that should be positive.
A norm
Of some state.
of some state.
Like out of time ordered fellows cannot be written that.
Mm-hmm. Yes.
So therefore there is no, right? I presume that it's only the time ordered guys like U, V, V, U
Yeah,
but not the other.
but the other one will, because it's an analytic continuation of the first one, so there will be
some
yes.
constraint.
Yes. Okay, so this is from a paper by Adams, Arkani Hamed, Dubosky, Nicolis, and Ratazzi. It's a 2006 paper. So this theory, if you just look at the vacuum of this theory, everything looks fine. There is no causality violation. But let me consider a non-trivial background or non-trivial solution.
When you say there's no causality violation, you mean all correlators arbitrarily high powers vanish at space-like separate points?
All.
What do you mean exactly by that?
So if you, okay, let me give you the classical argument. So then basically, okay, so this argument is going to be a classical one. So if you just consider simple solution, classical solutions, so you will not see any problem. But you can.
Specifically saying 2-point functions.
Okay.
It's going to look at linearized solution.
I mean, just because some other solution is a coherent state built out of a vacuum, so if it shows up there, it's much
Clear.
clearer.
Yeah.
Okay, so let's consider this solution where the C is some constant vector, constant time lag vector, and you can then consider fluctuations around this solution, and you can write down the equation of motion for that perturbation, which will have this form. You can just write down plane wave solutions of this kind. So you'll get a condition like this. Because C is time-like, you can actually figure out the phase velocity of this plane wave solution, and you can actually show that the.
Why was C time there?
Okay, so that's actually a very good question. Actually, in this paper, they consider time-like. They didn't actually explain why it has to be a time-like one. But what I think the answer is, if you take this solution and if you find out the stress tensor for this kind of action, you'll get something like a ideal fluid, but the velocity is a space-like one.
No, but C mu being a constant is a solution to the equations of motion for any C mu, right?
Yes, yes.
So is there some rule that says we cannot look at C mu space-like?
There is no rule, but if C is space-like, probably the stress tensor of this thing that's basically will be a ideal fluid with space-like velocity. So it's like a tachyonic fluid. Probably that's not a very valid solution itself.
So somehow the rule is that you're not allowed to look at it. That's
Yes,
wrong with that.
but yeah. So in the paper, they actually didn't clarify this at all. But I think that's the reason.
Or is it that the effect you were interested in shows up?
No, like actually, if C is space-like, actually you'll conclude that mu has to be negative, which is not true.
So maybe you can consider both kinds, but you get this conclusion.
Actually,
You just rule out all theories.
yeah, exactly, yeah. You'll rule out both mu positive and negative.
Both positive and negative.
Yes, yeah.
But could you rule it out? Oh, I see. You mean with time-like you rule out one sign and with
Just
space-like?
like you do.
Yes.
Okay. Oh, but you don't want to rule out.
No,
Yeah.
because there are real theories with one sign.
So
This is nonlinear sigma 1.
Yeah.
one consequence of that will be basically A theorem will be basically A is same for every
I
theory.
see. Well, I should let you go on, but as a nonlinear sigma model, you have higher derivative curves as well. Right? If mu is very small, you can still rule it out.
I think
I mean, is there a self-consistent argument which allows you to truncate up to 4 derivatives?
Yeah, I think so. You see, he's getting. I mean, anything else will be subleading at
Mhm.
small k. So the first correction to anyway, why doesn't he? The dispersion relation as in strength of k is given by this. goes outside the light cone, you have something higher order culture.
Yeah. So
Okay, we'll do one.
yeah. So if you want to have causal propagation, just from this you will conclude mu has to be greater than or equal to 0.
Actually,
So-
Sharon, I have a comment. I think only one particular sign of c square will give you will satisfy the equation.
For the
Re-
other side, you have to flip mu.
Oh, so you're saying just plug this in. Wait, but the equation of motion is something with two derivatives acting on any field, right?
Mhm.
So why isn't there always 0?
So if you take the second part, the 5 plus 4 part.
Any term I vary, I'll always have two derivatives acting on one field. So I've got a constant to satisfy.
Any constant satisfied. That's certainly true. Sorry,
Yeah.
what is the argument that mu has to be greater than 0? Because it
Can you
what are your conventions for the metric minus 1, 1, 1, 1? Or
minus plus plus plus, yes.
minus 1. Okay, and if mu is greater than 0, k squared turns out to be negative.
Okay, so let me.
Yeah.
So why does mu have to be greater than 0?
Okay, so if C is time-like, let me just choose this to be a C naught and 0. So this is just omega square plus k square C naught omega square. So basically you have
In effect, you're saying you're okay with the speed of sound being, light being less than 1.
yes, yeah,
Not greater than 1.
yes, precisely.
Okay. And what would have gone wrong if it were a space line?
So there will be a k over here.
It makes it bigger.
Yes. Okay, so basically the conclusion from this is that mu has to be
Wait, but the
Yes.
k would have come with the other sign, right?
sorry.
The k would have come with the other sign.
Yeah.
And that's what would have made it bigger?
No, but there is a square over here. It doesn't matter if.
Oh, I see. Okay.
So the conclusion from this is basically in Adams et al. Paper they concluded that if mu has the wrong sign, that means if mu is negative, then there is. So this coupling is basically a non-renormalizable coupling. So it's an effective theory. So they claim that if mu is negative, then there is no way you can UV complete this theory. This is one. There is one more way you can derive the same constraint. If you can consider 2 scattering of phi, and just from unitarity you can show that if you just demand unitarity and some condition about the fact that amplitude decays fast enough at infinity, you can actually conclude the same thing just considering 2 scattering. Yes.
So this requires that mu has to be greater than or equal to 0.
Yes.
If you have C time, then why is that not good? Sorry, can you repeat that?
So if mu is negative, that there is a problem. If mu is positive, it's all right.
Mu is negative, then positive.
What if you take mu negative and C space length? Don't you do the same thing?
Yes, but I guess you are not allowed to take C space-like, because in that case, you can compute the stress tensor for that solution. That will be. It looks like that has some problem because it's basically a tachyonic fluid.
And what was the thing about the after that UV completion?
So their conclusion was if mu is negative, that means this theory can never be UV completed, because mu negative means basically this theory is violating causality, so it cannot come from any Lorentzian invariant UV theory.
So if you integrated out a massive field with a
Mhm.
you're saying that it should always appear with mu greater than
Yes,
equal to 0.
yes, yes.
And so just can you write down the effective speed of light, please?
Okay. Let me. Okay, yeah.
These are not exactly physical solutions, right? They have infinite amount of energy, right? I mean, there's something a little, I'm not entirely convinced about this argument because with the space-like you make it a separate conclusion. I'm worried that you're not considering in the first place a physical solution about which you're considering the perturbation. It has infinite energy. You can never generate it in the laboratory starting from the lab.
It's infinite in the sense because it's the same everywhere.
Or do you have you probably have an argument that you have a bubble.
Yeah. That was the
I
argument.
remember from Shiraz's Journal Club something like this discussion.
But I don't remember in the journal club that there was this space-like kind, like.
So they actually didn't mention that in the paper.
But I mean, somehow I feel that you can just. Yeah, can you finish this?
Okay. Let me first check if my signs are correct. Yeah. So the omega.
Between the omega counts, so
Yeah.
C not having the order.
There's no omega square.
Oh, so yes. C square. So you have something like 1 minus mu half mu C naught square.
This is the
Plus, 1 plus.
1.
And omega, which one is the speed of light? This is the speed of light.
Yes.
This is the speed of light. So we don't want it to be minus. We don't want it to be plus.
This sign is correct, right? For C to go, no, yeah.
Oh,
it's not-
let me check.
Yeah, this is the one.
What was your signature?
It should be minus plus plus plus.
That's consistent with this.
Minus plus plus plus. Then why did you get minus omega squared plus k squared?
No, that's correct. For minus plus plus plus, it should be.
Yeah, that.
Key upstairs and downstairs for 0 component of opposite sign.
Yes, but then he started with a minus del phi square.
Oh, you think he's written that wrong?
Probably.
No, there's a correct sign to get phi dot squared from it.
Yeah, so phi dot square will come
This
with
is
positive
correct,
sign.
but
Mhm.
it's just, I think what is mu, whether mu is consistent with the mu here.
Okay, now
No, phi dot square should be positive, so that means the omega square should be positive, right?
no,
I mean,
but there is a
Phi
negative
dot
sign.
square is positive.
There is a negative sign.
Good, so that doesn't that translate to plus omega square minus k square?
Oh, I see what you're saying. So the equation of motion.
I
So
don't know how you're writing it. I mean, it's just in. Okay. Yeah, there's some relative.
Yeah.
And there
actually
the-
that K mu, I don't know. I don't know whether
I mean,
that's
with one sign you would take t minus.
So I think this should come with a negative sign. This k mu.
Okay. It doesn't matter very much. Fixed. If you just clear up the sign. I just want to check that the space-like thing is giving you the wrong thing. Are you totally sure of that?
Oh, so for the space-like one, basically this will be omega not
Can
k.
you just write on the speed of light and go?
Okay. But the thing is that I probably am getting the wrong sign for.
Fix
Yeah.
the sign, but relative sign if you get correct.
Okay, I see. For space-like, we'll get this. Let me just clear this up.
Let's say omega mu is. Yeah. Go on.
So for space-like, you'll get minus omega square plus.
So is this the right sign?
No, this is the wrong sign, but just
Flip.
okay. So I have to flip that for the other one too.
Plus mu c dot k will make it minus mu. Then
Okay.
algebraically
This
it's
is
consistent.
what
Yeah.
comes from the equation. Okay.
So this should be negative. Right? Yes. Okay.
Now
So
we
now
have-
this will be mu. Because it's space-like, let me just write this like c dot k.
So now omega square by k square. Once again you get reduction, right? Once again you rule out negative over mu.
Is that correct? Yeah.
What happened?
Even for space like you rule out negative.
Oh, it's the same sign?
Yeah, I think so.
No, but 15 must not be calculated.
Let me forget that. I'm just talking about causality.
The energy constraints are not, I don't know, physical. I mean, it's infinite energy. I don't know what to say. Okay, so, but anyway, it give you the same
Give you the same thing. Whether space like or time like, you get the same conclusion.
Yes, but I can make one comment there. So if like you can use similar kind of argument for del phi to the power 6 kind of interaction when you don't have del phi to the power 4th, then it has to be time like for.
Okay, that's another one.
Yeah,
Can we agree on the algebra? That the algebra tells you that both space life and time life are giving you the same.
Yes. Yeah.
Okay, fine. So then at least we'll get to del phi to the 6 later.
Okay.
But at least this.
Okay, now let me go to the second example. And this comes from gravity. Let's take this 5D gravity theory. So you have the standard Einstein-Hilbert term. Let me add a negative cosmological constant for later convenience. And I have a higher derivative correction term. So this is the Gauss-Bonnet term, which is ghost-free in 5D. And let me make some comment about all the coefficients. So C2 is order 1 number, and M2 is some mass scale which is below Planck scale. In the paper by Kamanho, Edelstein, Maldacena, and Zoviedov, they showed that if C2 is non-zero, then there is a violation of causality, which the argument is somewhat similar. So their classical argument is the following. You can have a solution like this. So that's the ADS part, and you can have a shockwave solution. So you can have something like this. This function is known, and UV, they are basically right cone coordinates. So this is in a diagram. Basically, this is this. If this is V, this is U. So there is a shock wave along this direction.
Sorry, at least there, if you thought of it as an effective field theory, there's no contradiction, right? That is at the level at which you get a violation. If you had a 1 over m2 to the cube or whatever term, that would be important, right? In other words, you're probing, you get the shockwave violation, you get the causality violation only when you probe energy scales of order m2 or time scales of order 1 over m.
Yes, yeah.
So only this was literally the whole theory.
Exactly. So if there is no correction whatsoever. So yes.
But here the claim was taller, right? That even though it's an effective field theory, you can draw a conclusion about the sign of the.
So
In some sense, it seems more.
So here there is no way you can fix, if mu is negative, there is no way you can fix it. There actually it's possible, like you can add other stuff to fix the causality violation, yes.
But somebody is asking classically, can you argue that this causality violation cannot go away by a del phi to the 6?
Yeah, that's what I was wondering.
First of all, that will be more suppressed. So that's.
I think if you take both C and K of the same order, it's small.
Then you lie securely in the.
I don't know, but this mu is a mass scale. That's your point. And your question is, can you take? You must only take. I'm not sure.
I mean, I can see why, because you're fluctuating the dispersion relation only by a little bit, right?
Mm-hmm.
Your point is anything higher is more irrelevant. I can see that.
But there's also this issue of the C, because you could saturate many of the other derivatives by C. So if you take C large, it's not clear that there is.
Then you know, but I thought the point being made is, for, as you said, for C and K both small, everything it seems.
Yeah.
Yeah, but if C and K are both measured in units of mu, then all terms would be comparable in that C.
But let's take C by mu and K by mu.
Very small.
Small.
Then this is the first
So
direction.
C is in my hand, so I can
Yeah.
take the C thing to be small,
And K
so
is-
that the other guys.
Yeah. Exactly. K is now quadratic.
Okay, so in this background, if you take a probe graviton along this direction, and if you just if this graviton just propagates in this background, what will happen is that when it hits the shock wave, there will be a jump.
I think the main difference is here you need to probe distances of order m2.
Yeah.
And there you do.
You don't, exactly. That's what I, yeah. That's right. That's right.
So this is. Now,
Just one
yes.
There's a beautiful dispersion relation proof of
Yes, yeah, yeah.
of the same. You just use the optical theorem and close a quantum. And it's a two-line proof. So independent of causality, just to prove this mu is. So certainly correct.
Yeah, there's a, yeah. If I have time, probably I can go over that also.
Yeah, I remember that.
Oh, I see. So you say that the difference here is that it's K square here and K fourth there. Is that the point?
The background that he used had to have, classically this thing happens only when these two things come near to each other of order m2. That's it. So, okay, then of course nothing, all that's up. Nothing was needed here. The background is totally independent of mu. It's not related to mu.
Which was possible to do.
Which is possible, and you see the effect. You see the. Another way of saying it is that, see, in gravity, ordinary gravity gives you a time delay.
Mm-hmm.
So, in order to beat that by high derivative correction, you need that high derivative term to be acting significantly to beat the gravity time delay. So, you need something of order alpha prime over here. On the other hand, here, the ordinary phi to the fourth theory didn't give you either time delay or time, you were on the light cone.
Right.
So, a small effect did push you off. I think that's the difference. Yeah.
Yeah,
The Shapiro time delay has to be beaten.
exactly, yeah.
And then that can only happen in a way that is not reliable.
And with the high derivative correction, actually you can do that. So that's the main point of the paper. So yeah, if you can just compute this delta V, and this delta V has to be positive from causality. So we just compute this delta V for and this graviton. Because the graviton, you can choose the polarization of the graviton. For one polarization, you can actually rule out a particular sign of C2. For the other polarization, you can rule out the other sign. So from here, they concluded that C2 has to be 0 to preserve causality for all possible polarizations.
And just to ask, do you find this argument entirely convincing?
So this one, you mean?
Is this an open and shut argument, or is there other issues?
In the gravity community, just this part of the argument, there are debates, because like they say this is not sufficient. Having a negative time delay is not sufficient. So you have to there should be some closed time like curve. Then they'll be convinced. But
Didn't these people then show you can build a closed time like curve? There's that part of the paper where they put together shock waves properly and they build a closed time like curve.
in that paper, I don't recall.
There is.
Lots and lots of stuff.
Oh, yeah.
It's a bit borrowed, but
Yeah, but that.
Two guys boosted. Two of these.
Yeah. But there was another paper by I think Harvey even after the games.
No, I read that paper. I was just wanted your opinion. Do you find it convincing?
So just this part of the argument, I mean, then that's
Do you find the result convincing?
The
Do you
re-
feel there is doubt or not? I don't know.
the result is convincing in the at least in ADS it's convincing in the sense that I can derive everything just from the CFT side.
So you have no doubts there.
In ADS, no. Okay, so because
No.
they also build a time machine which seemed okay to me at least.
It seems like, as he said, there are many gravity papers though
Yeah.
backing it in totally irrelevant grounds as far as I can tell. But just in case.
but still like it's not that issue is settled yet. I don't know.
It's not settled because the gravity people don't agree, but gravity people never agree about obvious things, right?
Harvey Real and so on.
No, but it was some very. Anyway, yeah, but
So the issue is whether the violation could be only local and you can recover it at large distances. But this issue has been addressed by Mollison and company.
Yeah, the time machine was made to do that, right?
other issues he raised also, but ever.
Yeah.
I remember I had the issues.
So let me make some comments about. Just let me one more. Just let me make one more comment. Actually, if you have other terms, this doesn't have to be 0. What it says is the following. Just if you do perturbation around some background, this theory will break down at a scale which is much higher than M2. What the argument in Kemp's paper is saying is the following. So naively, you will expect that the theory will break down at a scale which is parametrically higher than M2, but causality tells you that no, actually it breaks down at scale M2.
Why I would have thought even just naive, but because the small parameter here is momenta in units of M2.
Mm-hmm.
Two more derivatives in units of M2.
But there is like M Planck, this is outside. So basically, if you just do perturbation theory, the scale will be square root of M2 times M Planck, something like that.
Yes, the point is that there's a classical, that it's nothing to do with quantum mechanics.
Yes. Yeah. Okay. So now let me.
I mean, in perturbation theory in loops also you say it's M Planck.
Yeah. There's a coupling constant that can be taken to 0.
Mm-hmm.
So you push all perturbation theory effects to infinity. But there's a problem in classical physics. So it's irrelevant what happens.
But anyway, in classical physics, the theory will break down at momenta scales of order M2. Because you can have classical backgrounds where once the rate of variation of the background fields becomes M2, the higher derivative terms become important.
No, but suppose we postulate that this is the full theory. Classically, it could have been well defined.
Mm-hmm.
But even classically, there's a problem at scales M2.
Yeah.
I was just saying, there are two issues, I mean, in effective field theories breakdown. If there is a higher term, when
When
is
is
it
it
important?
important?
That is important classically
At
when
scale.
you have fields varying at order M2, that's all I'm saying.
Yeah, but there's a separate question, which is, could this theory by itself, with no other corrections, have been consistent
Mhm.
And then I think he's saying that just a classical argument tells you that it couldn't be consistent beyond it.
Mhm.
This,
Yes.
Yes.
So basically, yes, there should be some new physics that should appear at scale m2 to fix this problem. So what are the implications for ADS CFT?
So just to say, that means that up to the, if I truncated the Lagrangian up to this,
Mhm.
that couldn't have come by integrating out some fields starting from some good theory like gravity coupled to a bunch of
Yes.
massive fields. That would never lead to this.
Yeah. First thing that you can say about the boundary CFT is the following: the stress tensor 3-point function
Sorry,
Yes.
just to follow up on Gautam's question, a loop effect could presumably generate such a term, but you're saying it would generate more. Yeah. Thank you.
So what this says is the following. So because you are not, in fact, in their paper, they also had ruled out R cube kind of terms. So for, the boundary interpretation of that is the following: the CFT stress tensor 3-point function, it's actually just given by the Einstein term. By Einstein term, what I mean is the following: you can compute this in the ADS by computing, let's say, Witten diagram in Einstein gravity. That's the full answer. And there can be corrections, but they will be suppressed by the gap of the theory. Another consequence of this is the following: in 3+1 dimension stress tensor, there are two anomalies. Yes.
Hello. I mean, we cannot see the board actually. What is it?
sorry, sir.
Little pressure on those guys. There was a trial. It didn't go so well. Sorry, Laura. We'll fix this soon.
So in 3+1 dimension, you can have two anomalies, C and A. So just from the first statement, you can actually show that for holographic theories, A and C, they should be almost same. So there can be correction, which is suppressed by delta gap.
Those are 3-point functions, those are Einstein.
But what will you use to derive that?
So this part,
Huh?
it's just, let's say you can compute the this from Witten diagram, let's say this Witten diagram.
That's a computation, right?
Yes.
Why do you need to use this to get that?
So in principle, there can be, the 3-point function has contributions from R square or R cube terms. Because they are not there, so it's basically just, it comes just from the Einstein gravity part.
Well, what about higher powers of R?
R to the power 4, they'll not contribute.
Why not? Why can't the background of ADS saturate some of the R's?
Sorry, you can repeat that?
Let's say I have R to the power 10.
Hmm.
ADS background saturates 7 of the R's. Fluctuation gives you the other 3.
Oh, so they will be suppressed by.
Suppose my theory here. I mean, you've not ruled out the possibility of having an R to the power 10.
No.
So suppose my theory was not R Gauss-Bonnet, but R to the power 10.
Okay.
Then I put that in ADS. It's not clear to me that this cannot contribute to the 3-point function. Or is it true? With a coefficient that's independent of the mass scale.
I don't think 10 R to the power 10 this kind of terms can contribute to 3.
Why?
That let me. Yes, yeah, no.
So it's not obvious to me that you cannot have.
But I mean, they would also then contribute to the relation between RATS and lambda, right?
Okay.
I'm just wondering.
But could you arrange indices so that you get a different index structure for the 3-point function?
This is first. This 3-point function is fixed, like at least the tensor structure is fixed by conformal invariance. So
There are 3 possible.
yeah, yeah.
So the question is whether you could get some of the other term. That's the basic question.
Yeah, the answer, at least from the Kames paper, I think the answer is no.
I don't see the argument.
But
the Kamp's paper rules out
mhm,
3-point correction to 3-point functions in flat space.
mhm.
Is that enough to rule out correction?
So just let me just think. So the contribution that, as far as I remember, the contribution that comes, the contribution to A or C, I think they just come from R square and RT kind of terms.
Why? Maybe this is true, but why?
That I'm trying to.
Is this
I-
true? Does somebody know?
I don't have an answer right now. Probably I'll
I very much doubt it. Are you saying that if I knew just the first correction at the lambda equals 1, that would determine the 3-point function? Somehow I don't think that's right.
I don't have an answer right now. I'll check.
So, I'm just making a guess. Presumably, the statement is that there are three structures, and the 3 structures are already gotten by maybe like the first few terms, and if you are adding many more terms, maybe like to get the 3-point function, you can make the other terms not contribute by some field redefinitions or something. Is that?
So yeah, it's certainly correct. Just from conformal invariance, you can show that like there are 3 structures. One comes from Einstein gravity, and the other 2 basically.
I think one is parity validating, right? One of them is parity validating.
Yes.
So okay, that anyway, but yeah, even with parity conservation.
So those two other structures, they are actually ruled out. Just by itself, they are ruled out. So as probably I have to check, but I guess their statement was even if you have like R to the power 10, those kind of terms, you'll generate those structures which are ruled out. So they will not contribute to the Einstein.
So then there's some separate argument in ABS.
I think, Shiraz, the point is that the other structures are the things which lead to this problem with the time delay. I mean, anything which leads to other structures would lead to a problem with the time delay.
Yeah, but you can't use flat space for that, because R to the power 10 wouldn't contribute to the 2 to 2 graviton scattering in flat space.
Mhm.
So it would have to be a new argument within ADS to make that claim. Yeah, so, and perhaps it's true, but I just wanted to hear what this situation was. It's not like you can import the flat space argument to this, because the flat space argument was essentially about 2 to 2 scattering.
Mhm.
But I would imagine that like we can define, say from the CFT viewpoint, okay, there are 3 structures which are possible, and I know that there are 3 kinds of terms that we can add to the action and do a weighted diagram computation to get these 3 structures.
Yes.
Then presumably I can define the coefficient of those, those 3 terms to be the 3 structures that I should eventually get, that they should not get corrected.
Yes.
Right? I can use that as a definition of the couplings, which is basically fixing the field redefinition partly or in some way, right?
Yes. And then you would have to argue that with this definition, any coefficient of the other 2 structures violates causality.
Yeah.
This is not immediately clear from the flat space argument. It may well be true, but it requires some further step, right?
Mm-hmm. Yeah.
Okay.
But that doesn't need R to the power 10, right? We can make the same argument with the Gauss-Bonnet, for example. Right?
No, but I thought the logic was that we know that Gauss-Bonnet cannot be there in flat space. We've got some huge ADS, so it cannot be there in ADS either.
But this one is actually in ADS. This argument is in ADS.
Which argument?
So this the shockwave argument that was in ADS.
The Schoff paper.
Shockwave.
The part of the paper I read had it in flat space, but
But
maybe you can also make it in ADS.
yeah, yes. In I guess in section 5 or something, they like at least the shockwave argument they reproduce that in ADS.
I see. Okay.
Yeah. So this solution this is basically a solution in ADS.
You ruled out only what, R square?
In the paper, they actually also ruled out R cube.
I mean, if you can show that any structure in this 3-point function that's not the Einstein structure violates causality, then of course you're done.
Mm-hmm. Yeah.
But that would essentially be a CFT argument.
There is a safety argument.
There is one. Yeah. So basically, but to that point, so if you just want to derive this from the CFT side, that's obviously this cannot be true for any CFT. First of all, it should have large n. And even that's not sufficient. You should also assume that the spectrum of low dimension operator is sparse, and that even it wasn't a priori it's not even clear if that's these two assumption if they are sufficient to derive something like that. But it turned out it's sufficient at least up to some caveats that you can actually derive this from the CFT side.
You'll explain this to us.
Yes. Yeah.
Okay, fine.
Okay.
This is the caveats are ignoring the double trace exchange.
Yes. Yeah.
That's a big caveat.
Yes. Okay. Okay. Now let me just move on to quantum field theory. So by causality in quantum field theory, what I mean is the following. So this commutator vanishes when they are space-like separated. Again, I want to stress that this is an operator statement. So if I insert this inside any correlator, even that should vanish. And a consequence of that is basically it's possible that this is, if you compute this in a vacuum state, it's 0, but in some non-trivial state, you can compute this quantity, and it can turn out to be non-zero, and there can be a problem.
I'm really sorry, I'm still trying to process what you were saying in response to Shiraz. So just from a CFT analysis, can you show if the 3-point function had other index structures that it violates causality?
So from the
Just as a field theory question.
So what we can show, so this we can show up to a caveat about double trace operators that if so in general the stress tensor 3-point function has 3 structures. Let me call them A, B, and C. For this A and C, they are the anomaly coefficients, and this B is some other term which is not, otherwise not, it doesn't have any name. So just from the causality argument, what you can show is the following. You can show that B should be 0 and A should be equal to C. And that's exactly what you get from Einstein gravity.
I see. And this is, so you take the Euclidean CFT and you continue to the Lorentzian space and then use causality.
Yes, yeah.
But just to say, the way they do this is to take the one conformal block corresponding to stress tensor exchange. And they show that that block has trouble. But there are an infinite number of other blocks corresponding to double trace exchange, which are ignored. So the possibility that those blocks fix up the trouble
Oh, I see.
is left open.
Mhm.
I mean, it's probably true, but it's not yet.
Yeah, there is no proof of that. Yeah, there is no. Yeah.
It's not completely. There's no completely convincing argument. It seems to me from
Yes.
this field.
This is not a 4-point function. You still break it up into blocks.
You look at a 4-point function.
Mhm.
You look at a 4-point function. Look at contribution of that from 3-point
TT.
TT.
Your point is TT. Anything else, double trace,
Mhm.
Yeah.
could be giving a contribution.
Also gives a contribution. So there's the really nice observation is that just the TTT block it works very nicely by itself
Yeah.
if you have only the Einstein exchange. Anything else has trouble, but the possibility that the double trace exchange could cure that trouble is left open. This is a serious possibility because clearly when there are higher spin net, when you have alpha prime corrections, they are the ones that do cure the problem.
So yeah, one thing for sure, they do contribute to the 4-point function for sure. So, but the thing, so that's not even a question. Like you can actually show that they contribute to the double 4-point function. But the thing that can happen is that basically we had to smear all the stress tensor. So one possibility is that after smearing, only the stress tensor block is somehow the most important term. But that again, there is no proof.
It's probably true, but it's not yet.
Yeah, there is no proof. Yeah, there is no, and it's probably not very easy to show either.
Just to understand, even with the assumption of the sparse spectrum, the double trace thing is just two gravitons. Is just
Yeah.
two T's, right?
Yeah.
Mhm.
I see. Thank you. Sorry.
No, I'll go over it, I guess, with more details later. Okay, so now let me make some comments on Euclidean correlator and how to get the Lorentzian correlator from the Euclidean one. So generally when you compute a Lorentzian correlator, what we do, we start from some Euclidean correlator. So this Euclidean correlator, they are single valued, and as I said earlier, they are permutation invariant. You are allowed to switch the orders because in Euclidean signature operators do commute. Also, if this Euclidean correlator is analytic as long as there is no it's non-analytic only when 2 points coincide. Otherwise, it's nice and analytic. And also, if all the points are Euclidean, then there is no branch cut. So just from if you want to go to the Lorentzian correlator from the Euclidean one, you do the standard analytic continuation. For tau, you just pick one spatial direction and you just perform an analytic continuation.
Sorry, what was the remark? If all the points are Euclidean, then there is no branch cut. What does it mean?
So
I mean, it's a certain function
yes.
in the complex plane for all the x's.
Yeah, so as long as in the complex plane there can be a branch cut, but if these points are real, then everything is fine. Like there is no branch cut and there is no.
Remove the cuts, are they? Is that not to lie on the real axis?
Sorry?
The branch cuts can be chosen not to lie on the real axis, is that?
Yeah, that you can do, yes.
I mean, there is a square root. I mean, there is a square root, 1/3 root, or whatever it is in the appearance of the function, whatever that function is. And what does this statement mean?
So I can give you an example. Probably that will be more clear.
It just depends on modulus.
Yes.
Is it just that is a well-defined function? The Euclidean correlator is a well-defined function. You don't need to.
So there is no ambiguity anywhere. It's a single valued function.
If you want to analytically continue it, you have issues.
Exactly.
On the real sheet, just totally well defined. Like 1 over mod x1 minus x2 to some power.
So there is the good old reconstruction theorem, which tells us that
It's like 2D CFT, right? Final operator spectrum is mutually local. That's what we normally say, mutual mechanics.
so there is a reconstruction theorem which tells us that if you start from well-behaved Euclidean correlators, and if you then analytically continue that to the Lorentzian signature, then the Lorentzian correlator will be well-behaved. So, and by well-behaved, I mean it should obey certain condition, again analytic, from the coincident points.
Away from light cone.
But it's Euclidean, there is no light cone.
I didn't understand. What was the question? What are you trying to show?
So it's basically the reconstruction theorem says that if your Euclidean correlator is well behaved, and by well behaved I'm
Well behaved of
yeah.
You're giving the condition.
Yes,
on
yeah.
top
What
of the
I mean by well behaved, yes, yeah. So let me write Euclidean.
But analytic will just mean no singularity. There's no complex analysis here.
No, yeah,
So there's no singularity. That's a well-defined function apart from coincidence.
exactly, yeah. This is SOD invariant in D dimension. Also crossing symmetric, a permutation invariant.
Permutation then just means it's a function, right?
Yeah, precisely, yeah, just function, yeah, nothing more than that.
Say that, it's just a function. Yeah, okay.
But because crossing symmetry is kind of important, that's why I'm just keep.
Why is it a statement without content? If f of x1, aren't you saying f of x1, x2 is the same as f of x2, x1? That's
If
not just following from.
that's
Wait, if these are, let's say for a moment that these are 4 different operators, then that's not true.
but if
Then it's not true. Sorry, what is the statement of permutation invariance? Is it that
it's basically you're just allowed to or in terms of in a CFT I can explain it better. So you're allowed to expand in different channels in CFT.
even for equal operators?
For equal operators, if it's a function, it's an obvious statement. You
No,
not change the correlator.
No, but I'm just saying even for even for equal operators, I say, okay, I take a 2-point function without assuming any translation invariance or anything to begin with, and I take the 2-point correlator and I say, okay, it's a function of x1 and x2, the 2 points.
Right.
Now, just as a math statement, f of x1, x2 need not be f of x2, x1.
Correct.
So he's just,
Yeah, it's
in that
the
case, he's just
In that case, when
Yeah.
the operators are equal, then you get the same object again by interchanging.
by permutation.
Yeah. But in general, if you have n different functions, there's no such statement, right? I think it just means that you take the one operator around another, there's no partition. I don't really understand.
so this is what like in a CFT what I mean is the following. So if I have 4 operators, let's say sorry, I can just expand in conformal blocks like this, or I can expand.
No, now you're bringing in new elements. You're bringing operator product expansion
Yeah.
and so on.
So otherwise,
About the statement about correlators, what is this?
it's basically like if it's let's say a 2-point function, it's basically you are allowed 2-point function of same operators. You are allowed to just exchange x1 and x2. That's
No,
it.
Wait. So there are also the other quantum numbers like O1 x1, O2 x2 being the same as O2 x2, O1 x1. That's just is that the statement that you are making, or are you saying O1 x2, O2 x1 is the same as O1 x1, O2 x2?
No, the
What
first
are
one.
you doing with the operators?
The first one, I guess. So
The first one. So
Yeah.
it is O1 x1, O2 x2,
Mhm.
is the same as O2x2 O1x2.
Yeah, precisely, yes.
Yeah.
So I'm also, sort of exchanging the quantum numbers wherever they were.
Yes, yeah.
But that sort of.
You're just saying it's a function.
Yeah, it's just
Yeah.
a function.
That's all you're saying, right? There is a function of x1, x2, x3, x4, and if some operators are equal, then there's certain symmetry.
Yes, yeah.
Okay.
Yeah, there is nothing more than that, yes,
Okay.
precisely.
I agree. If all operators are unequal, I don't know what the statement
Yeah.
is.
And it's not true. It's not true. I mean, O1x1, O2x2.
If you have
So
some
it
other
says
operator.
O1x2, O2x2. So the quantum numbers remain the same, and x1, x2, whatever.
And the fourth condition, which is actually very important, that the correlator should be reflection positive.
You're going to explain that.
Yes. And after anti-continuation, this gives us a well-behaved Lorentzian correlator. And again, there is one more condition that we didn't have to use, and which was actually a part of the reconstruction theorem. It's basically how fast it should decay if you go to infinity. But that's not very important for us. So let me just remove that. So for the Lorentzian correlator, it should be unitary and causal and Lorentzian invariant. So in some sense, if one question actually which is kind of important is the following. So if, let's say, in a theory causality is violated, so what goes wrong in the Euclidean theory? Because causality is a Lorentzian concept, you will not see that directly in the Euclidean correlator because you don't have light cones, but there should be something which is wrong in that Euclidean theory, and I'll try to explain that these two reflection positivity and crossing symmetry, that will, if I give you that in the Euclidean correlator, the theory will be causal, at least for a CFT.
And unitarity, what about unitarity? That may be easier because roughly is the fact that the Hamiltonian is Hermitian. Maybe you map that. What is the map of unitarity?
There is not a very direct map, but reflection positivity is because it's about positivity of a correlator. It's something similar to unitarity. So that's one, but I'm not sure if that's the only one.
So you explain reflection positivity?
Now, yeah, I'll do that. Yeah.
Sandeep, there's one more statement I would say that, like on the Euclidean correlator side, isn't there also an assumption about the spectrum, which is kind of like crucial because, for example, in the case of string world sheet, that is the assumption that fails, which makes it so difficult to implement the epsilon prescription in the world sheet. Okay, so I mean, so you're just implicitly assuming this statement that the spectrum is well behaved, that it does not have a Hagedorn like growth or anything like that.
At least in the reconstruction theorem, I don't think they had to assume anything like that, but it might be hidden there. But I don't think they had to assume anything like that in the reconstruction theorem.
Yeah, the reconstruction theorem is just a theorem about analytical dimension.
Yes, yeah, precisely, yeah. It doesn't tell you anything more, yeah.
Yeah, but analytic continuation may not exist if your functions are not well behaved. I think it's probably related to this statement that he made about how the functions are behaved under near infinity. Because which is really at how the things are behaving at very high energies, Euclidean high energies.
Yes.
And string theory has a very like non-quantum field theory like behavior, high energy behavior, which makes analytic continuation much more subtle in string theory than in quantum field theory. This is the thing that Ashok has been like Ashok and Witten and so on and so forth have been talking about. This is the problem of I epsilon prescription in the world sheet. Right?
I think that's hidden in that fifth condition that I erased, probably.
Could you state it then? What is the
It's basically, I don't know exactly. It's basically it should decay at the.
And decay how fast?
How fast that statement I don't know by hand. Yeah.
Yeah, I think the statement is that the worldsheet correlators, the worldsheet, sorry, the calculation that you do in worldsheet obey all these four, but it doesn't obey the fifth condition.
Okay.
So, and then the fifth condition is in some sense more interesting because there is an example which we all believe is physical, which seems to violate it.
But the
Sorry, but isn't, I thought string theory amplitudes were softer. Don't they die out faster? Than powers, for example, die out exponentially and so on? Isn't it better?
Yes, they do.
I see. That itself causes the problem, is it? The subtlety?
Yeah, precisely because they die off, they are much better than quantum field theory. It's one of these complex analysis things that you can't. If something dies off too fast at some direction, that shows up in some other direction.
Yeah. E to the power minus s is worse at infinity, worse in the complex plane than 1 over s. Because 1 over s dies off everywhere in the complex plane, where e to the power minus s blows up somewhere. That's what you're saying.
I see.
But sorry, Loka, this must be something about space-time, right? On the world sheet, isn't the theory just a normal garden variety conformity theory?
Yes. What I mean by it is a statement about Euclidean calculation.
But the analytic continuation of the space-time field somehow.
Yes, yeah.
Okay, fine.
But the reason I mentioned worldsheet is that you have to ideally you would want to do that in worldsheet somehow. But the point is that if you try to make the worldsheet Lorentzian, then you run into problems. You should never make the worldsheet Lorentzian. You have to
make the worldsheet and space-time Lorentzian at the same time. That's what you're referring to?
Yeah, so that's what you would expect. But then if you try to make the worldsheet Lorentzian, so we would like to continue in space-time, right? We would like to make the space-time Lorentzian, right?
Yes.
Okay. Now the natural thing to expect is that you just make everything Lorentzian, including the worldsheet.
Yes.
Okay. But that doesn't work because for this reason, which means that you should keep the worldsheet Euclidean, okay, and only make it partly Lorentzian. Only make the asymptotic part for the worldsheet Lorentzian and not the internal part for the worldsheet. Which is what makes the analytic continuation much more subtle. Because you cannot just make everything Lorentzian.
So then you're dealing with non-unitary theories and various such things, right? Because you analytically continued space-time but not the worldsheet.
It leads to unitary theory. You can prove unitarity by, this is Ashok and Roji's proof without actually completely going to the Lorentz in this thing.
No, but just the worldsheet theory is not unitary because x0 has the wrong sign.
Oh yes, the worldsheet theory of course is not unitary, yes, because it has, yeah. But that's just a side comment, and we probably not jump into the discussion here.
Okay. Let me now comment about this analytic continuation.
Wait, you're going to explain permutation, reflection positivity to us?
Yes, I can do it now or like
Whenever, but
yes. I can just give you the statement if that.
Sure.
Okay. Yeah, the statement of reflection positivity is the following. If I have operator. So the correlator like this, they should be positive.
Now it's restricted to 2-point functions?
No. You can have as many as you want, but yeah. Just yeah. Yes.
Okay. There's a request to move the camera.
Yeah. So.
And when you say for any point correlator, you mean
Okay, let me.
Endpoint correlator and two theta ones.
So basically, yeah, it's
In here and in there.
yeah. So whatever I write here, I should write the same thing on the right side with time flipped.
And you're assuming that this O is some Hermitian operator, or I mean some reality condition, you know? Otherwise you need the O star.
Yes, there should be a star. Yes, yeah. Yes.
Okay, and from just I just want to understand where this condition comes from.
Mm-hmm.
The way I'm thinking of it is that if everything's working right, I can think of a state on the tau equals 0 axis created by the path integral from the bottom half plane. I get the complex conjugate state from the top half plane.
Yes.
And then this is the inner product of a state with itself.
Yes.
And therefore true.
Yes, precisely. Yeah.
So this tau 1 and minus tau 1 is probably not really relevant. I mean, I could do radial quantization in which I could just reflect about the unit circuit.
Yeah.
And then instead of tau 1 and minus tau 1, I would do that kind of
Yeah.
thing.
Yes.
And then this O1 star will be defined appropriately outside of the
Yes. Yeah.
unit circuit.
Yeah. You can do that. Yes. Yes.
But I suppose that's most natural for a conformal field theory, where this is more.
This QFT.
Yeah.
But why is it? Go ahead. Can I ask what exactly is the definition of Hermitian conjugation in Euclidean theory?
It's just complex conjugation here.
Start.
Yeah. Yes. To start. Yeah.
Think of it as insertion in a path integral, you're inserting the complex conjugate insertion.
But why, from the point of view of a wave function, you are evolving from minus infinity to tau minus tau 1 for the first part, is it?
I think evolve all the way up to 0. Put the insertions, but look at the state at 0. So that whole path integral defines the state at tau 1 equals 0. And it defines a bra at tau 1 equals 0, and these are exactly complex conjugates.
But the evolution is a Euclidean space, right?
Yeah.
And you evolving in, this is Euclidean, right?
Yes. This is
You're
Euclidean.
evolving in Euclidean space, let's say from minus infinity
Mm-hmm.
to 0,
Mm-hmm.
and inserting the operator at minus tau 1.
Yes.
The other one you want to think of by time reversing. You want to think of the full evolution from minus infinity to infinity by flipping it, is it?
Yeah, think of it as an inner product. I'm thinking of this
Yeah.
is creating one state, this is creating another state. And
I can probably on Friday I can probably give a brief argument like why this is positive, but yeah, it's basically what you said. Yes.
So without other operators in the middle,
Mhm.
it would be exactly a norm square.
Yes. Yeah.
With other operators, I have to again have a pairwise or what? I mean,
So
whatever you do at the bottom, you do the same thing at the top. And then still a norm
Mhm.
square. Norm square for different state.
Yeah.
So it's that kind of correlator that I have to think of,
yes.
which this is what you had said earlier,
Yeah.
which can be thought of as norm square.
It's non yeah. So because it's Euclidean, so basically it's they call it reflection positive, but yeah, it's basically norm squares. That's why I said like that's why I think unitarity is related to reflection positivity.
You know, norm square is a perfectly well-defined concept, whether it is Lorentzian or Euclidean or whatever. I mean, I have a Hilbert space
Mhm.
in which with a positive definite inner product.
Mhm.
That has nothing to do with whether I mean I can think of some group representation
Mhm.
on a unitary Hilbert space, unitary that has no concept of Lorentzian or Euclidean or something. It's
So-
just saying that the representation of this quantum field theory operators, whatever that this representation is, it's a unitary representation.
Yes. So basically, yeah. So I guess your comment is that I can just say this is a positive, like norm is positive. That this statement is that. Yeah.
I'm just
Yeah.
rephrasing what you said.
Yeah. So basically, yes. That like the name is generally they use the name reflection positivity, but yeah, it's basically positive norm state. Yeah.
So I didn't understand that though. Isn't it? I mean, when the whole Hilbert space picture comes up, only in Lorentzian space, right, or not?
So,
I mean, is Euclidean space some trick analytic continuation of the actual part? If you just have Euclidean theory, there's no Hilbert space.
transform it. I don't really have to sort of, I can slice it any which way I wish.
And then you think of this as the liver. Okay, I understand. Sorry, yeah, I can hear you.
The way that you describe the reflection positivity, it doesn't seem to me to be testing the Hermitian nature of the Hamiltonian sort of equilibrium in Minkowski space as much as some kind of a time reversal invariance. I mean, what you're saying is, what you're basically saying is you take the Hamiltonian, which you were evolving as e to the minus I h t, you evolve it as e to the minus h t from say 0 to infinity, or well, okay. I mean, isn't it more testing the fact that you go up, but you think of cut it at half point, and the rest of the going up you think of coming down from the top, which is like a time reversal. That is, in terms of the notions of the Lorentzian theory, it seems to clearly test something about the Hamiltonian. And
isn't it testing that e to the power I h dagger is e to the power minus I h? Because you're evolving this way with e to the power minus I h, and you're evolving that way with the other one. Which the analytic continuation of those two would be e to the power e to the power h t and e to the power minus h t. I think it's testing that h is Hermitian, effectively. Because suppose we take the Lorentzian calculation, and then Euclidean continue that. In one you're evolving with e to the power I h, the other you should evolve with e to the power minus I h. Or really, if h is Hermitian. I'm not 100% sure. I think so. You wouldn't be U dagger if h was not Hermitian.
yeah.
Yeah, I'll go for it probably next day. Okay, now let me just make a few comments on the analytic continuation.
And apparently there are plenty of stat-mech models that are not reflection positive. Is this right?
I'm not sure. No, is that correct?
All these non-unitary minimal models presumably are not reflection positive.
Yeah, no, if it's non-unitary, then it's possible. Yes.
Yeah. So stat-mech has no notion of unitarity. It's just some.
But I'm not sure if the connection between unitarity and reflection positivity is like that direct or not. Like
That's what I was trying to ask, because
there is.
I would have thought it is, but you were saying it's not, and I was wondering why not.
So no, like it is related, but I'm not sure if that's the only only condition.
Well, let's take the stat-mech models that are well known. Let's say these non-unitary minimal models. Clearly, they obey all your other conditions, which are almost non-conditions.
Yes.
So the invariant, permutation invariant, all obvious things. The only thing that can fail is reflection positivity. You're saying all these conditions are obeyed, they would be unitary. We know they're not unitary. Therefore, reflection positivity must be failed.
So for that example.
Those are all Euclidean models, right?
Yeah.
So, in a Lorentzian sense, would it be the case that, and they're not reflection positive, and you're saying in a Lorentzian sense they always fail with unitarity?
We know that they fail with unitarity. Let's say I take the non-unitary minimal. We know they're not
the linear model, the Ising model in a imaginary magnetic field.
Sometimes the word unitarity is used in different contexts. Does it actually mean unitarity in the Lorentzian sense when you say they're not unitary?
I mean, there's no positive. The norm matrix is not positive. It's not just the unitary blocks that you see. The way
Unitary representations of okay. What's the notion of when you say it's in Lorentzian space the theory is unitary? What do you mean?
Basically, I loosely mean that basically if I write it as a norm of some state, it should be positive. So more precisely what I mean, basically the correlata, they should obey Feynman axioms, all of them.
But in these non-unitary models, there's this classification of all unitary representations of the conformal algebra, and some of the representations that appear are not unitary.
Yeah, that I understand. That's just a statement of there's some definition of in any group of unitary reps which involves positive norms.
Yeah.
But I was checking because on the right hand side we have a notion of unitarity which has to do with Lorentzian Lorentzian space and so on, right? Not
Yes.
vector groups and so on.
Yeah.
So that's a slightly different notion, although involving positive norms.
So this is I guess the right statement. There is no proof that like this, like you cannot just like from reconstruction theorem you cannot just prove that if you have a non-unitary Lorentzian theory only the reflection positivity will.
You say one of the conditions must be failing,
Yeah.
and it seems to be that the other conditions.
No, I said like there is no like
there's no
proof.
Like,
Yeah.
in model by model, all the other conditions
Yes.
must be obviously true.
Yeah.
So it must be reflection positivity as well. All the other conditions are only conditions almost that only mathematicians would list. Right? I mean, they're almost obvious. Hard to believe any reasonable statement model fails the other conditions.
Yeah.
The only one that could fail, I would imagine, is reflective positivity.
In those cases.
In those cases.
Yeah, that's true. But I thought, okay, sorry, but at least one part of the conversation was whether that maps to a failure.
This is another. I was just asking a more basic question about whether these models fail to be reflection.
Mhm.
Yeah. Okay. Thanks. Loga?
Yeah, so just maybe I'm just trying to rephrase the question. If you had a primary with negative dimension, conformal dimension, would it fail reflection positivity?
Yes. Yeah.
Okay. So a negative central charge would also fail reflection positivity.
Or if it's positive.
The negative central charge would also fail reflection positivity. Is that right?
Can you repeat that?
Negative central charge would also fail reflection positivity. If you had a let's say a conformal field theory, central charge negative,
yes,
less than 0, then it would fail reflection positivity. Is that a correct statement to make?
That sounds right, but I'm not 100% sure.
There's one more question which you probably just to ask it anyway. Whenever I talk to my condensed matter colleagues, specifically Kedar, he always says reflection positivity means ferromagnetic couplings and non-reflection positive means anti-ferromagnetic couplings. Do you have any idea what this means?
So it's not a statement of the permissionness of.
I cannot ever understand this, but
No.
he has a way of thinking that seems very useful. I'd like to make connection. I'll ask him.
Okay.
I'll ask him in front of you.
Okay.
Both of them permission.
Let's do some StatMech. Saying when a StatMech model has ferromagnetic couplings, it will turn out to be reflection positive. When a StatMech model has anti-ferromagnetic couplings, it will turn out to be non-reflection positive. Because he said to me about 10 times, I've never understood.
Just that's the thing that's confusing me, that from the Euclidean theory, from those kinds of points of view, the StatMech models, I mean, it's more natural to have a non-Hermitian Hamiltonian of some sort if you're going to have a violation here, but not a violation of positive norm, right? Whereas the unitarity in the Lorentzian space is tying more to a statement about norms rather than Hamiltonians.
But sometimes these things are not distinct. Because if you're willing to put I's, then you can make everything a machine at the expense of introducing a negative norm. Right, for instance, what's the difference between SO 4, 2 and SO 6? Either you can say it in the sense that the norm, you know what I mean? I mean, if you're willing to redefine the inner product, you can make everything in a machine. So sometimes it's not an invariant thing to discuss. Both have to be true.
Okay, let me make some comment about analytic continuation, which is going to be important for the discussion.
I mean, basically, converticity is a condition that involves the norm.
There's one issue which is implementing the positive definiteness of the inner product of the Hilbert space at t equal to 0 or equivalent to tau equal to 0, let's say. That's one thing. Is there something additional to that is being said that about the time evolution or the transfer matrix evolution? So I think this is a weaker condition, right? that we are dealing with Hilbert space of positive definite scalar product at tau equal to 0 or t equal to 0.
Okay.
And then something further is being said, presumably, about the theory.
Yeah.
So like, the Hamiltonian is realized as a Hermitian operator on this tau equal to 0 slice or t equal to 0 slice. And yeah.
But I think this reflection positivity condition has some of it. Because it's the same straight from bottom and top requires that
it should be flipped.
That exactly. That the complex conjugation is doing only flipping of time.
Yeah.
And that seems to be saying that H is Hermitian. Otherwise it would be different states.
Yeah.
Right? I mean, I don't know how much what implies what, but I think some element of that is right. I think your condition would be just for insertions with infinitesimally near t equals 0. Then you wouldn't need.
Yeah, then I don't need. Then there's just a statement of operators on that slice.
Yeah.
But then I'm coming down.
Yes.
Yeah.
So then you've inserted, then you evolve, then you insert, you evolve.
Yeah.
So to start from the Euclidean correlator, you again do this anti-continuation. So before I do that, let me make some comment. So in the complex tau plane, the structure, Euclidean correlator has a very intricate structure of singularities and branch cuts. So because of that, so this anti-continuation is ambiguous, and that's not a bad thing because the different choices that you can make for this analytic continuation, they will correspond to different operator orderings in the Lorentzian correlator, and there is a one-to-one correspondence. So that if you can perform analytic continuation in n different ways, then in the Lorentzian side, basically you can write down the same correlator in n different orderings. Yes.
Basically, I get where these branch cuts come from. Is there a way to see it mathematically where they come from?
I think it's just that the continuation, the fact that the correlator singular Euclidean point, a coincident point, the analytic continuation of coincident point is a latch.
Let me give you an example. It will be clear.
Right, because x square equals 0 is Euclidean point.
So let me give you one example which will be useful. Let's say I have this 4-point function. This is some random direction, and this is Lorentzian time. You have one operator over here, O1, O3, and O4. Let me draw the light cones. And there is another operator O2 somewhere here, let's say. And I can move this in this direction. So when O2 is here, it is basically everything is space-like separated, so there shouldn't be any problem. So there is no ambiguity in analytic continuation. So in the complex tau2 plane, where tau2 is the Euclidean time coordinate for operator O2, so this is how where the singularities should be. So the first singularity that will appear when this will hit this light cone. So that will be somewhere here. And there should be obviously another one in the lower half plane. So there will be a branch cut. So then.
Wait, just to get the coordinates in your diagram.
Okay, yeah.
Y is one of the spatial axes.
Yes.
T is.
This is Lorentzian T.
Lorentzian T.
Yeah.
So your points are separated on just one direction in space.
Yes.
And in the imaginary direction in another direction.
Yeah, but only one of the like all the other operators, they are t equals to 0. Just one operator which is at finite t.
Fine. cut emanating from 0, I thought it would emanate from where it comes to light code.
Yeah, so here, yes.
So why have you drawn it?
Oh, so this is complex tau 2 plane. So this is real. So this is the Lorentzian time.
Oh, complex tau 2 plane.
Mhm.
So it's saying, I see, at t equals 0,
Mhm.
but tau 2 equals 1. Thank you.
Yes. The next one will be when this hits the second light cone, the light cone of O3. Let me just write down O1 here, because this singularity is from O1. So there should be another one from O3. Similarly, there should be another one for O4. And let me.
You're keeping y fixed as you move. In this
Yes, yeah, y is fixed. So y is fixed, and it's basically let me y equals to half. Let's say.
So your x-axis is now real time, the real tau.
Real tau 2, yes.
Yeah, real tau.
So this is basically the Lorentzian.
That is Lorentzian, that's you.
Yeah. Yes.
But why did you say you also had a singularity at negative t?
So because like this light cone, you have this, right? So if you just go,
But you won't hit O1 at least, okay?
you will not hit O1.
You will hit something else.
Oh no. So
O1.
yeah. Sorry.
You have two light cones.
Yeah.
Okay, got it.
So basically you're saying that O2 has a singularity with respect to O1
Mm-hmm.
of the kind which is like tau 2 square plus y2 square
Mm-hmm.
whole to the power some delta or something,
Mm-hmm.
and that becomes now t2 square minus
Exactly.
y2
Yeah.
square whole
Yes.
to the power delta.
Yes.
And there are two places where that can be bad. One is equal to plus y thing and minus.
Let me just write down where it is. It's basically
Pass light code.
y2 minus y1. This should be at I. y3 minus y2. Now, if this operator O2 is inside the light cone of O1 or O3 or O4, so for example, let's say, let me just erase this. Let's say I want to start from the Euclidean one here, and I want to analytically continue it to somewhere here. Because of the branch cuts, there are many ways you can do it. So let me now write down the rules of this game. So whenever there is a singularity, you can either go, you can pass the singularity from the right or from the left. So if you pass the singularity from the right, that will put this operator. Let me go.
Sorry.
Yes.
If this is separated, it's at a certain real time.
Mm-hmm.
So the singularity will be at y squared plus t squared minus tau squared. Let's call t the real part of time
Okay.
and tau the imaginary part.
T is
Or whatever, whichever way. Right?
Yeah.
Okay. Y
so
squared.
tau.
So y
Euclidean, yeah.
squared plus t squared minus tau squared.
Yes.
Let's say the singularity with respect to the
Let's y square plus tau e square minus t square.
So it seems to me that the end point of this branch cut is a curve on this plane, not a point. This going to 0 gives you tau squared minus t squared is equal to y squared. No, t squared minus tau squared is equal to parabola, right, or hyperbola, whatever.
So what
Let me not class the branch cut or just the branch point.
Mhm.
Isn't that a curve on this plane?
branch point? Yes, but like basically.
So, sorry, just 1 minute. Shiraj, I think there should be imaginary part, there should be t tau, plus 2I t tau, or something.
Oh yeah. Oh, it's tau e plus I t e square of that.
Plus I t tau, what happened to t tau term?
Oh, thank you.
Yeah.
Thank you. You're right. Thank you. Sorry.
Yeah. Okay.
So it has to be purely real.
Yeah, so there should be.
And that's, as long as that's non-zero, it's not zero. Thank you.
Okay, so the rules are the following. So if you pass a singularity from the right, so in the resulting Lorentzian correlator, that will put operator O2 in time order with respect to the other operator. So let me draw another diagram. If you have a branch cut like this, if you pass it from the right, let's say this is O1, this is O2. If you pass it from the right, that will put O2 in time order with respect to O1 in the resulting Lorentzian correlator. If you cross it from the left, it will be anti-time ordered.
How do you tell which is which?
Oh, it's okay.
Why is that the case?
Oh, so that you can basically figure out from the reconstruction theorem. You have the I epsilon prescription. From there, you can just check which one is what.
So, but like just for a simple 2-point function or something, reconstruction theorem.
So basically, there is that I epsilon prescription that
Yeah.
exactly tells me like.
That okay. If positive frequency, I mean, at root for something simple like a 2-point function, you're saying you can see from here the positive frequencies propagate to the future negative. That comes out in some obvious way.
There is one easy explanation that I can give you.
Yeah.
So that I epsilon prescription, what it does is the following. I have to guess something. Okay. So in this language, basically, I'm not changing the position of this operator. So what I epsilon prescription does, it fixes the analytic continuation. So that's basically this one. But it moves the operators in the real direction, something like this. Because that's where that epsilon comes from. So basically, from that you can actually figure out like if it's crossing the singularity from the left or right, and which is time ordered, which is anti-time ordered.
So, is this a statement about any state? Is this a claim about any state that this prescription will work?
You mean there is a proof, or?
And he's asking
Yeah.
only for vacuum correlators.
Is this a statement just about a vacuum correlator, or for example, with a finite temperature correlator, this will work too?
For finite temperature, I'm not sure, but for vacuum correlator, like finite temperature correlator, I'm not sure. Yeah, I think. Yeah, otherwise I think it should be valid. Because it's not that we proved it that this is you can check that this is exactly the same as reconstruction theorem. It's not that you can prove it exactly, or we didn't try that.
So say again, what is reconstruction?
So basically,
After Douglas done.
Yeah. I guess what I'm asking is, what is the assumption of the state in the reconstruction theorem? Is the assumption that any state is fine, or you're only reconstructing the vacuum correlator, Lorentzian vacuum correlator?
The reconstruction theorem basically tells you like if I give you an Euclidean correlator, what is the procedure that you should follow to get a particular Lorentzian correlator. So in that sense it's a statement about the vacuum correlator. So I can actually I can state that if
I see. So there isn't it says that if you go around like this and like that, you get the time order.
yeah. So let me just I think I can.
Suppose that the I epsilon prescriptions come out right for the time order.
Yeah, so this is the from reconstruction you get this. If I want to compute this Lorentzian correlator, x1, t1. So this is basically this quantity. And you take the limit epsilon 1, all the epsilons they go to 0, but in this order. So, but epsilon 2 is greater than epsilon 1, and this is.
Wait, is there a T somewhere in that equation, time order or something? Or what is the?
Which side?
Reconstruction theorem tells you how to start from the Euclidean correlator and get, say, the time order correlator in Minkowski.
Yes. So basically, yeah. So that's precisely, but you can compute this from the Euclidean correlator, which is unambiguous.
Any particular order, not just time.
Yeah, any ordering. Yeah. So if I want to change, yeah. If I want to, let's say, change the ordering, all I have to change is basically the ordering of epsilon. Which one is larger, which one is smaller. That's it.
Yeah. Sorry,
you mean? Wait, I don't know. Is the left hand side the Minkowski?
No, this is the Lorentzian one. Yeah. Yes.
This is the Lorentzian.
Yes.
This doesn't have a time. This doesn't come with T1 bigger than T2.
One of these two is time
No.
ordered, the other one is not. One of these two is, one of the ones that he gets is time ordered. The one which he's taken from the right is time ordered. But the one from the left is not. Because
What's the right one looks like?
the right is this one. So this theta 2 went like this.
No, but forget that. Here he is giving a prescription, right? Take T1 plus I epsilon T2 where epsilon 3 is bigger than epsilon.
Yes.
What does that give you as far as the Lorentzian is concerned? The right hand side is Minkowski.
It's Lorentzian, but this one, if you.
Alright, it is Lorentzian, but as a limit of a Euclidean.
Exactly.
Right?
Yes. Yeah.
Okay, so if I did this limiting procedure, what do I get on the left hand for the left hand side? I don't get some particular ordering.
Yeah. So you get particularly this one. Like that, it's basically not a time ordered one. It's basically exactly the way I've written it. This is the ordering of the Lorentzian correlator.
Oh, suppose
It's a general Weightman correlator, I think, right? It's a general Weightman correlator. Any general Weightman correlator, you can get it this way.
Yeah.
Not time ordered.
No. Any. So basically, okay. Let me.
Unique time ordered correlator. But he's going to get many different correlators.
Yes. I can just change how the relative power value of epsilon 1 and epsilon 2. That will change the ordering.
I have a way of thinking of this prescription, and please tell me if it's correct. Either you're going through the cut or you're not.
So which you're talking about this prescription?
The right going to theta 2, theta 1.
Okay. Yes. Yeah.
Say right means not going through the cut.
Exactly.
Left means going through it.
Yes.
Now, not going through the cut should give you just a natural time order.
Yes. Yeah.
And that's what you're saying.
Yeah.
Not going through the cut is giving you time order. Going through the cut is violating the time order.
But right now there's no time order. My point is you don't have a T on the left hand side, right? This wasn't the answer when T1 was greater than T2.
No.
So you can ask whether it agrees with the time order correlator. So for one ordering of times it agrees, in the other one it does not. So if we had theta 2, theta 1, see theta 1 is before theta 2.
Yes.
So time ordering would put theta 1 on the right and theta 2 on the left.
Yes.
So that right prescription is giving you the time order thing.
T1 is bigger than T2 or not?
Yeah. So okay. Let me. That
T2 is bigger than
O1 that's at t equals to 0.
An equation and the figure. Which one are we looking at?
Figure. I'm looking at the
Alright, which figure are you looking at?
Okay. There are.
Okay.
T2 is bigger than T1.
Yes.
So then theta 1 should be to the right.
Wait, on that figure,
This O1 that's exactly at t equals to 0.
T2 refers to Lorentzian time on the y-axis.
Right.
Yes.
Okay, in that figure, the time at which theta 1 is inserted is bigger than the time at which
No, theta 1 is inserted at t equals to 0. So this.
Then why is it off on the?
So that's basically because of the. So this is exactly this position is at I y2 minus y1. It doesn't depend on.
Sorry, isn't the y-axis? What are we drawing there?
So this is basically when basically my operator O2 that hits the light cone.
Yes.
So the actual operator O1 that sits at the origin. Yeah. So where that's at t equals to 0. So when I write down this operator here, that's basically at t equals to 0.
Okay.
And this one at this, whatever this analytic continuation tells me.
Okay.
So here also I have the same thing.
Okay. I'm with you now.
Yes.
So the rule is very simple. It says if you want to go out of time order, you need to pass through a branch.
Yes.
And this is also very, very natural, because natural Lorentzian correlation functions are just automatically time ordered. If you want to do something out of time order, you need to go on a different contour. So going through the branch graph is taking you on that different contour. Is what you're saying. That's very natural.
Yeah, there is one more point to that. Basically, like it could have been possible that after this analytic continuation, you get some combination of different orderings, but that's not true because like the discontinuity across the branch cut. Yes.
Sorry, but that's fine, but that's not what you're saying here.
In what? In the equation?
In the equation. I mean, where in the equation are you pointing out how do you go around anything?
No, in that equation you don't have to. That's in reconstruction theorem. Basically, the analytic continuation is fixed. This one. So basically, you're just moving around your operators.
Maybe I can make a comment here.
Yes.
So suppose I put epsilon 1 equal to 0. Let's suppose I put epsilon 1 equal to 0.
Okay.
So
Yeah.
And then epsilon 2 being positive means that tau 2 is slightly positive. So I'm starting from here. So this is actually tau 2, right? So I'm slightly here.
Yes.
So that is how this diagram relates to this one. And if the tau 2 is positive, in order to reach the y-axis, you just go like that. And on the other hand, if this tau 2 is negative, which is the other order in which the other thing happens, then you are coming from here. So the epsilon fellows are just the taus themselves. And he's saying, okay, so this is just the.
I mean, you are saying that had you taken epsilon 1 to be 0 and epsilon 2 to be positive.
Yeah, if epsilon 2 is positive, then this arrow that is being drawn there is on the right side.
Then you would have computed.
Then I would have computed
theta 1,
O1,
theta 2.
Yeah. And if I started from the left.
And if epsilon 2 is this, then you would have computed theta 2, theta 1.
Correct.
It's basically in one prescription you're keeping the operators fixed and you're just changing the contour of analytic continuation. In the other one, basically you're fixing the analytic continuation and you're just changing the position of the operators.
But I mean, what I'm saying is, if epsilon 2 were greater than 0 and epsilon 1 is 0, you would have computed theta 1, theta 2 regardless of whether T1 is bigger than T2 or T1 is less than T2.
Yeah, it doesn't depend on T1 and T2.
So that prescription of epsilon is not at all tied to time ordering or anti-time ordering. It is tied to, that is,
unless T1 and the two operators are time-like separated, the ordering doesn't matter. Because they commute with each other.
yeah.
It's only when they're time-like separated that you have to worry about which order you're worrying about.
That's true.
So it's only when T1 is greater than, when you've gone past that light cone that you have to worry about what the order is.
Just, yeah.
But what I'm saying is that, wait, I'm having a bit of trouble here. I mean, if the sign of epsilon 2 is not correlated with the, I see you get O1 and O2 as long as epsilon 2 is greater than 0, right? In that order.
Yeah.
Regardless of the time difference between T1 and T2.
Yes.
I see. But it corresponds on that figure to going one way or the other. If T1 is bigger than T2 or T2 is bigger than T1.
Yeah. So in one case, basically there is no, it will not never cross a branch cut, so it doesn't actually matter.
Sorry, okay, I'll have to do that in my head. I see. So depending on whether T1 is bigger than T2 or T2 is less than T1, choosing epsilon 2 to be greater than 0 means you go one way or the other.
Yes.
I haven't followed the discussion with the epsilons, but final prescription sounds very natural. It's just the statement that we all know the statement that time-ordered correlators are natural analytic continuation of Euclidean.
Yeah, that's fine.
So if you want to get just a time-ordered correlator, you shouldn't have to go through some branch.
Exactly. Yeah. Precisely.
So everything, when you're going in time order, you don't go, you go to in the simplest route without crossing any branch. Every time you cross a branch cut, you flip it. That's the pattern.
That I understand. I just wasn't able to, not quite able to derive that from here.
I haven't followed the epsilon test.
I have just one more comment to that. So as I said earlier, it could have been possible that like after crossing a branch cut, you get a mixed correlator. That's not, you don't get that because basically the discontinuity across the branch cut, that's basically the commutator.
How do you know that?
So you can just compute that from 2 point, like you can just do that from 2-point function and.
But is there a logical reason that the discontinuity was the? I was just actually wondering about exactly the same thing. The discontinuity. Did I know that the discontinuity?
What is the statement? The discontinuity or the branch cut is?
That's the commutator.
Because the difference between the two.
And
it sounds like a statement I should have known, and maybe I do know it, but in some
I know that example by example. I'm just trying to figure out if that's a more general statement than that. One, it should be first of all it should be related to the commutator up to a factor, because you should get non-vanishing commutator not before you hit the branch cut. So it should, the commutator should be proportional to the discontinuity in that sense. If you don't hit the branch cut, the ordering shouldn't matter. So in that sense, but I'm not sure about the overall factor, like if that's fixed or not.
I think from your Lorentzian picture there, the overall factor is also fixed, right? Because just look at the expectation value of the commutator of O1 and O2. Which was exactly when you go across the branch cut, it becomes a commutator. Before that, it's zero.
Right.
So the commutator clearly has that discontinuity.
Yeah, but he was trying to rule out that if you go through the branch cut, you get O1, O2 plus O2. How do you know that that's not? You see, without going through the branch cut, it's clear you get O2, O1. After going through the branch cut, the question is how do you know that you get so the consulate is right.
That's important. Yes.
I think going through the branch cut is like, like if you're doing a diagrammatic, it's like cutting a propagator, right? In some sense. So it's like picking the residue of the epsilon prescription.
Yeah.
Because you're subtracting out the thing with plus epsilon and thing with minus epsilon, right?
Yes.
And that you can use the Lorentzian formula to make it into a delta function.
Yeah. Yes. Yeah.
Okay. So then it's like picking up the residue of a propagator. I mean, I'm talking about a diagrammatic sense. Let's say you have a diagram in which you're calculating this correlator. Then it's like picking up the residue, and we know the residue is related to basically the commutator.
Yes.
So I think I don't know whether that is helpful.
It's closely related, I agree.
Yeah, it should be related up to some numerical factor or something.
The question is that like if you go to higher point function, the structure of commutators is also very intricate. So it depends on what kind of commutators, because how do you nest the commutators and so
Yeah.
So Sajid, I have one question.
Yes.
What is the place where this is described? I mean, in proof?
What you mean reference?
Readable reference.
It's in our 2015 paper, and I don't think I don't know if it's anywhere else. So I can actually write down the reference. It's 1509.
I'm confused as well. Hey, but Sandeep, you missed lunch.
Right.
So maybe just come to a natural stopping point and then we can continue.
I can, okay, let me just, in this language, let me just tell you the causality condition, like what causality means. Let me, I'll stop there. Okay. So let me exit this part. Okay, let's consider this correlators. When this hits, this crosses the first light cone and it approaches the second one. So that means.
So by the way, why did you choose the direction of the branch cut to go up, for instance?
Yeah.
Up. What do you mean? Like exactly upwards?
Upwards, why not down, for instance?
Even if you let me see.
Because down is where the invariant distance is positive, right?
Yeah, right.
And also this part is fully Euclidean. There shouldn't be any.
Should not be.
Yeah.
It should not cut.
Yeah.
And what about? Does it matter? Does the
Yeah,
direction
why
matter?
not going?
No, that doesn't matter. That doesn't matter actually.
That doesn't matter, but then
The prescription will be a little different.
Will be different.
Yeah, little different. Yeah, but it's exactly the same thing.
No, but then the question of left and right becomes more.
So now I can talk about left and right. Then basically I have to talk. I can talk about just crossing the branch cut or not.
Okay.
Yes. Yeah. It's yeah. So this left right that's
So
little
that's the
mis-
invariant.
yes.
Yeah.
So in that way, even taking it down should not create a problem.
No, it shouldn't
should
cross.
cut
Yeah,
the-
yeah.
It should nowhere cut the space like separated.
Exactly.
But
Yeah.
like just speaking mathematically, I can always move around the branch cuts
Mm.
unless.
Yeah. Mathematically it shouldn't matter. But yeah, you're not allowed to do that. But mathematically it shouldn't matter.
Yeah.
Okay. So I'm just considering this correlator where O2 is in the light cone of O1 and it's approaching light cone of O3. So basically that means I'm in this picture I'm approaching this singularity.
Yeah.
If I just do this regular continuation, it is obvious that the singularity structure is very trivial because you are not crossing any branch cut. This is basically determined by the light cone.
Yeah.
But what you can do, so this will give. Oh, let me even make it simpler. Oh. And you can perform another analytic continuation, which is this one. And you can approach the same singularity, but after crossing the branch cut. But after you cross the branch cut, it is not very clear if the singularity is should exactly be here, because it's not obvious. But it might happen that the singularity, after you cross the branch cut and go to the second sheet, it might move up or it can move downward.
Why is this position is fixed anyway, right?
I'm sorry?
The position of OC is fixed anyway, right?
Only on the first sheet. That's what he said.
On the first sheet, it's fixed by the light cone. But if you cross the branch cut, it's not. So it's a because you're crossing a branch cut, you can end up with a different function.
So it's not as if O3 and O1 O2 have to become. So I thought the point was that there was a branch cut only when you went from space-like separation to time.
Yeah. So I'm considering this correlator where psi is now time-like separated with respect to O. That's why you're crossing the branch cut.
Okay.
You're considering the particular correlator where you have to go to the second sheet.
So the second sheet is this whole story of space-like separation, time-like separation is not valid anymore.
No, but if it's time-like separated, only then you can go to the second sheet. So only then you have to cross the branch cut. So the point is, if it moves in the downward direction, that means, if it moves in the upward direction, that means the commutator becomes non-zero at a later time, and that's allowed. So this first case that says there can be a time delay. But the second case where it moves in the downward direction, that says the commutator becomes non-zero at an earlier time. which is not allowed, because that means operator. Do you want to repeat it? I can repeat it.
I know the condition.
Okay. So if it moves in the downward direction, that means basically commutator becomes non-zero even when they are space-like separated. So this is not allowed. So the causality condition is on the second sheet, this singularity is not allowed to move on the downward direction. And basically I'll show that in a CFT that comes from the well-behavedness of the Euclidean correlator, and it can actually impose constraint in various 3-point functions. And
presumably the reconstruction theorem is the statement that more generally than a CFT, reflection causality means that it never comes out, right?
Yes, because if it comes out, that means it's acausal, and that's not allowed. Yes.
So where do we find just an abstract mathematical proof of the reconstruction theorem? Not necessarily for CFTs.
In their 73, 75 paper probably.
Have you read it? Is it readable?
No, it's not readable. Probably Hag has some, not the whole thing, but the textbook by Hag, it has things.
PCT, spin statistics and all that, all those books don't have all this.
No.
Okay.
Oh, Hag. Okay, I can stop here, yeah.